can I say? Because I wanna be a boyfriend. Hey, little girl, I wanna be a boyfriend. Sweet little. Can we have the camera? Here we go. Oh, maybe we have it here. You have it there? You have it? Yeah. The switch thing. Good morning, everybody. Thanks for coming. Holiday weekend, kind of a pain. Didn't expect to see too many, but I did bring donuts for those of you that came as a little reward for coming in Monday morning. We have to give the lecture. It's a work day for us. Anyway, we don't get the day off at Cal. We get the day off tomorrow. So we have to talk. So we'll try and make it as useful as possible. We'll try to give you some hints on what's going to be on the exam tonight. And we have discussion, as you know, at 11 today in this room, and I will do that, and we'll try to give you lots of direction for what to focus on. But the exam, actually, I remember taking exams. It's no fun to take the midterms in college. I did it. I have a degree, just several of them, despite what you may have heard. And it still gives me kind of, an upset stomach to think about the chemistry exam. I probably couldn't even go through the topics without, a little, it's going to cover entropy. So I won't even do that. We'll try and do it in the course of the talk. So where are we in the roadmap of general chemistry? Last time we were talking about the bigger picture of the relationship between products and reactants in a global sense, in that why does anything happen in the first place? So we've understood that there's an energy difference between products and reactants, and in general, we expect things to occupy the lowest energy state over time. That's a stable state. We talked about stable states. It takes energy to go to any other state. That's what makes things stable. So this energy difference is certainly a factor in why reactions happen. But we saw last time there's another important factor, and that's the entropy change. So we talked last time how we could statistically determine entropy changes. So you would literally count the number of ways you could arrange something. And remember, entropy requires many states of the same energy so that the system can switch in between them with no energy penalty. And if you have that, and you have multiple states, billions and billions of equivalent energy states, then that is a high entropy state. And high entropy states are the favored states of the universe. That's the direction the universe heads, is towards high entropy, towards things spreading out. So here's just a ball bouncing, hitting the floor, and when it hits the floor, that potential energy in the ball is changed into kinetic energy, and then some of that kinetic energy is transferred to the particles in the floor. And those particles in the floor start moving randomly, and you'll get heat energy here, some random motions of particles. So this concerted directional energy transferred into random energy, and that ball will continue to bounce, and it eventually comes to a rest because of this energy transfer. These collisions cause energy transfer, and it robs the ball, the system, of energy. So this is the natural progression of things. And there's entropy there. There are these particles in the floor and in the ball moving randomly now. that weren't there before. So in a sense, the energy of the ball is dissipated into random motions. And that is one of the essences of entropy, dissipation of energy into random states. What we don't see, and we've talked about this before, are the random motions suddenly becoming concerted motion and making the ball leave the floor. We never see that. But all those particles moving in one direction is still one of the allowed motional states of those particles. They could do that. There's nothing in physics that says you can't all move in this direction instantaneously. That's one of the motional microstates. But it's only one. That's the lowest entropy state of all the particles moving in the same direction. And statistically, that's just nearly impossible to happen. So we don't observe that happening in nature. Same thing with hot and cool systems. We've talked about this, if you bring a cool system in contact with a hot system, those temperatures will equilibrate. Heat moves from a hot system to a cool system naturally, and it never moves from cool to hot. Or from any one part of the system, does heat flow to another part of the system and make one part cool and another part warm? That's part of the distribution of microstates throughout the system. So bringing two objects of different temperature in contact with each other, we know that intuitively they attain the same temperature, and heat always moves from the hotter system to the cooler system. In fact, that is a statement of this second law of thermodynamics, this increasing entropy in the universe. Heat always moves from the hot system to the cool system. So counting microstates, though, is a hard way to look at entropy. We can sometimes easily imagine one state has more microstates than another state. The classic thing is the liquid going to the gas. There's lots of microstates in the gas and fewer microstates in the liquid. And we know they're the same energy state. The particles can move back and forth in between those two states. The liquid has the high potential energy, but the gas has the high kinetic energy, but those energies can be interchanged. So there's no energy penalty at equilibrium for being in the liquid or the gas. But the gas phase has the higher entropy because of the number of microstates. So we can do it in general, we can imagine the cases, but actually counting the microstates is generally impossible. So the statistical definition of entropy, the natural log of the number of microstates, is a difficult one to apply. So we have a thermodynamic definition, and we're not going to go through how we arrive at this per se, but we know the terms. The change in entropy is given by the heat that either enters or leaves the system. So we understand that very well. And it's the heat along a reversible path. That's not particularly important to us, but reversible paths are equilibrium paths. So if you're going from the liquid to the gas in equilibrium, that's a reversible path over the temperature that the process occurs at. So we could talk about it for that cool going to warm situation. You could say, well, the change in the system that was warmer, the hot system, is the heat, and that we're going to give that heat a negative sign because that's going to go out of that system to the cool system. So that's leaving the system. The same amount of heat arrives at the cooler system, but it's at a different temperature. So if you do this and you say this process occurs at the higher temperature, this process occurs at the lower temperature, and you say, well, that is the system in the surroundings, or that's a closed system, you can add those two up. The hot temperature is higher than the cold temperature. So if you could either call this your whole universe or your closed system, but the sum of those two things is greater than 0. So the entropy change for that process is greater than 0. Why is this greater than 0? Because that T here is a bigger number than that T there. So you have this negative component divided by a bigger number than this positive component divided by a smaller number. So the sum of those two things is greater than 0, and that satisfies the universe. So these kind of processes, hot to cold, are consistent with our understanding of the entropy change of the universe for all processes is always greater than 0. What if the temperature does change? If the temperature just does change, you can just break it up into a lot of infinitesimal constant temperature processes and add them up. So if you say Q reversible over T and just, I'm going to integrate, that's the process of breaking it up into tiny steps and adding them up. You don't have to know anything about that in this class. But how do I get that reversible heat? Well, we know that too. We looked at calorimetry and we said, how do things absorb heat? Well, they absorb it based on their heat capacity. Some things have a greater capacity to absorb heat than others. And Q is the heat capacity times the temperature change, times the amount of stuff. MCP delta T. That is how you would get Q. So if you do that integration, this is just some math, you get this formula here. So if the temperature does change, we can calculate an entropy change from the heat capacity of the system times the natural log of the ratio of those two temperatures. So this is really interesting. The entropy change is related to the heat capacity. That's a little bit counterintuitive to think about. Why is that? Well, there's one way to rationalize it. Remember we talked about metals, that all metals have about the same heat capacity because they're just arrays of atoms. So all metals from an entropic standpoint look about the same. They're just ordered arrays of particles. And all metals have about the same heat capacity because of that. And this whole idea of that order in the heat capacity, that arrangement of the particles, the number of microstates in the particles, comes into the entropy. We understand that, and it makes sense that it would come through that heat capacity. Those two things would be related. The ordering of the system shows up in the heat capacity, and then it's reflected in entropy changes as well. All metals look about the same. You have the same entropy changes in those systems. So that's a kind of an interesting result. This is actually really beautiful fundamental property of nature. And if you study chemistry, you'll look at this in detail in your thermodynamics classes. This is a beautiful result. We just care that we can use it to get entropy changes when the temperature changes. Okay, so let's do a Chem Quiz then. About this, we'll take an ideal gas and compress it isothermally. Oh, Karen has a demo to watch this, not this happen, but Karen, you can come out and do our entropy change. Well, let's just wait on it, Karen. Never mind, we'll do it in a minute. We'll link it to something else in just a second. Let's do this Chem Quiz first. An ideal gas is isothermally compressed. How does entropy change in the surroundings? Let's talk about that for a minute and see what you think. If I could have up on the top, if I could have the tablet projected.
Never ever thought I would. You know you make me feel so strong. But now
Sorry. Yes. Yeah. So compressing it, you've got the right idea there. You've got more bouncing, but the bouncing isn't coming so much from the actual reduction in volume. It is in a fundamental sense, but if you push down, the surrounding is doing work.
Doesn't the energy like go into the
Well, the energy goes into the gas immediately.
into the system?
Yeah, that's where this extra bouncing comes from, the work that you did on it.
Surroundings should lose energy.
Well, we did say it happened isothermally. So you did that work. That would make, if it's a gas, that's energy in. So temperature would have to go up. But we said no, isothermal. So what keeps that process isothermal if I do work? If I do a joule of work,
Has to go out.
I could lose a joule of heat. Yes, I could take a joule of heat into the surroundings. So that's what's going on. Joule of work in, joule of heat. And Q reversible over T says that coming into the surroundings, from the surroundings perspective, that's positive heat. So Q over T says, yeah, yes. And it kind of has to happen because you kind of know if you decrease the volume, that's fewer microstates available. So that entropy went down. So the entropy of the universe better go up.
If it was of the system, we would say less.
Yes, if it's isothermal, yes. Use your voting machine to enter our thought if you haven't done so yet. We'll see what you're thinking. Many of us are thinking that the entropy of the surroundings increases greater than 0. Why are you thinking that? Well, the entropy of the surroundings is any heat that might enter the surroundings divided by the temperature of the surroundings. And this is the classic process that we have talked about many times now. If you squeeze that gas, you do work on the gas, so you've increased the energy of the gas. Your work energy goes into the gas energy goes up. If the gas energy goes up, what has to happen to the temperature of the gas? Everybody, you should shout this to me. If you take nothing else home from Chem 1, if you put more energy into a gas, what has to happen? The temperature has to go up. You have no choice. E is 3/2 RT. So, but I said isothermal. Well, that doesn't make sense. I'm saying the temperature doesn't change. Well, we're just not done. It's okay if the process continues and a joule of heat leaves the system to lower the energy and keep the temperature the same. So what's that? A joule of heat leaving the system, joule of work in, joule of heat out, temperature stays the same, but that joule of heat out is going into the surroundings. And that is increasing the entropy of the surroundings. From the surroundings perspective, that heat is positive. It's coming into the surroundings. So Q over T says that that is a positive number. And I'm not going to give something away. First, I will go to the next one. What about the entropy of the universe for that process? So let's think about that for a second. We're going to change the process. We're going to expand the gas against a vacuum and ask what happens to the entropy of the universe. Let's just talk through this one together. So now I'm going to let the gas expand against a vacuum. So if you expand against a vacuum, how much work is done? 0. So that is nice. Expand against a vacuum, no work is done, so the system doesn't have to use any energy, so its temperature doesn't have to change. No heat has to flow necessarily. So I get that work for free. That's free expansion. And I can say, well, free expansion, the system doesn't have to do work. It can attain that system with no input from the surroundings. Doesn't need to absorb heat. So this process is a process where I get free expansion for free, no energy change. And this is the system we talked about yesterday. Why does that happen anyway? Why does a gas naturally expand into a vacuum? We know that the energy doesn't change. So it wasn't energetic. It was purely entropy. It was purely an entropic effect. There are more microstates when you went to that bigger volume. You should distinguish in your heads entropy and energy effects. They are completely separate. You can always look at the entropic part of a process and the energetic part of the process completely separate, and you should disentangle them in your head. That expansion, the entropy increased. There could have been an energy component. Heat could have flowed in. There could have been an energy component, but it would have been independent of that entropy component. So if the entropy of that system increases, if I go up like that, the surroundings doesn't care at all because there was no heat flow. Didn't have to do anything. So the entropy change of the system, entropy change of the surroundings, 0. The surroundings doesn't have to do much. So increase in entropy here, increase in the entropy of the universe also goes up because this is in the universe. So the total entropy increases in that case as well. And we know that was the whole point of this gas-free expansion. That increases the entropy of the universe to do that. So if you're paying close attention last time, this would have been pretty obvious to you. So it's isothermal free expansion, entropy of the surroundings 0, no heat flows, system entropy increases, but the system entropy is the universe entropy because no entropy changed in the surroundings. In the previous case, that'd be the more interesting chem quiz. Maybe we'll put that one on the exam. Think about that. That previous case, we compressed the system, and we said, well, you compress the system, and we asked for the entropy change in the surroundings, right? So entropy of the surroundings, that heat flowed in, that increased the entropy of the surroundings. But you could say, well, what about the entropy change in the system when I compressed it? Is that an increase in entropy or a decrease in entropy when I compress it? Yes? It's a decrease. There are fewer ways. If you give it less volume, there are fewer microstates. Okay? Less space is always less entropy. So you give something less space, lower entropy. But I could ask you on the exam, not this exam because we didn't talk about it till today, but next exam, I could say, well, how big is that entropy change in magnitude compared to the surroundings? We said the surroundings went up. We're saying the system entropy went down. Which one has to be bigger in magnitude? Which has to be the bigger change? The system or the surroundings? Surroundings, why? What's that? Of the universe. Both those things are in the universe. So the entropy of the surroundings went up. The universe likes that. Entropy of the system went down, but it must have gone down less than the surroundings went up. Okay? So it's the entropy change in the surroundings driving that process. That's why that process can go. You would say to yourself, well, that process can't go. That's a decrease in entropy. How can that ever happen? Well, you have to take into account the universe. The surroundings entropy went up more than the compression reduced the entropy in the system. That's the nature of the universe. Entropy is not conserved. You keep getting more in every process that occurs. Fundamental and beautiful thing. Karen, let's come out and do this demo here. I'll just quickly, we'll talk about this a lot more later. But here's that classic case, liquid vapor equilibrium, high entropy state, low entropy state. Get that ready to go, Karen, and I'll, as soon as I get done talking here, we'll do that. So liquid vapor equilibrium, we could calculate the entropy change in the standard state. If it were in the standard state, and I was preparing this, what is the pressure in that cylinder? What? Who's saying 1 atmosphere? Someone? Ah, yes. Why, Sarah, do you say 1 atmosphere? Oh my God. Sarah says, well, that's the definition of the standard state. Yes, it is. Have another donut. So, yes, the standard state means everything there. Every gas is at 1 atmosphere. I don't care if you're a product or a reactant or what, that's what the standard state means. 1 atmosphere or 1 molar concentration if you're there. The liquid just has to be there as a pure liquid. That's the standard state of the liquid. But high entropy state, low entropy state. This reversible heat for that process is the enthalpy of vaporization. So delta S for this process is a well-defined, and this is equilibrium, so it's even reversible. That's the reversible enthalpy change. Over the temperature of boiling. If you do this at the boiling point, take the enthalpy of vaporization, divide by the boiling point, that is the standard enthalpy of formation. And if you plot that for various gases, you find out, plot boiling points versus enthalpies of formation, it's a straight line. This is a constant. The slope of that line is a constant. And that should make a little bit of sense to you. Things boil at a higher temperature because they have a higher enthalpy of vaporization. So those things go up accordingly, and that makes that constant slope. So the energetics make sense, but the entropy makes sense. Entropy doesn't care about really the energetics. It just cares about the fact that one of the systems is a gas, and that's very high entropy, and one is a liquid, and that's low entropy. So all vaporizations should have about the same entropy change. It's a purely entropic effect. Gas particles here, liquid particles here. Okay, so Karen can demonstrate, she's not going to demonstrate this in particular, but she's going to demonstrate something that is counterintuitive. Again, she has 2 salts, 2 solids. She's going to mix them together. Go ahead, Karen. She's going to mix them together, and a reaction is going to occur between those solids. And what's going to happen is a little unexpected. We're going to mix those together. A reaction will start to happen. This is a spontaneous reaction. The reaction goes with increasing entropy of the universe. That's all that has to happen spontaneously. So the entropy of the universe is increasing while this is going on. And we have 2 solids, and you'll see that it's creating a liquid-ish. It's getting gooey. So we can see there's a counterintuitive entropy going there. We're getting kind of this liquid state. But the entropy of the universe must be going up. So this reaction is very endothermic. We have an increase in entropy of the system, so we have to have a decrease in entropy in the system. We got a liquid forming. That means the universe entropy must really be going up. And it is, we have a endothermic process here. The entropy, energy is being absorbed by this system to counteract this disorder forming, and the water is so cold that the water froze to the block. So the water's freezing to that block. That's a very endothermic process, yet it happens naturally. And it happens naturally because entropy drives that reaction. The entropy of the universe is increasing when that happens, and we have a dramatic example of things can be spontaneous, they can happen naturally, but they don't have to happen with a decrease in energy. You can have energy coming into the system, endothermic, but still spontaneous. So that's an important lesson. It's actually the lesson of the day. So we'll do all this in discussion. One more thing I want to talk about is standard molar entropy. So we had these standard enthalpies of reactions. We had standard enthalpies of formation. We can also get a standard molar entropy. It turns out it's an absolute number. Remember delta H, you have delta H, and the zero enthalpies of formation are relative to the elements in their standard state. We set those at 0. And then we take the enthalpy changes with respect to them. For standard molar entropies, it's a little different because we actually have a 0 state that everyone can share. It is the perfect crystal. So if you take the solid, it's perfectly arranged at 0 Kelvin. That entropy state is 0. There's only one way to do that. So there is a perfect 0 in entropy. The solid crystal at 0 degrees K. So we can actually calculate then entropies of formation. We don't have to do all the comparisons to the elements in their standard state. We can calculate a real number. And how would you do that? Well, you'd go to the crystal at 0. And of course, you have to imagine this part. That's impossible to do. But you could say, well, let's warm that up until it gets to its melting point. And we could calculate the entropy for that step. It's a temperature change times the heat capacity of the solid. We could get the entropy, and it would be the area under this curve. So you'd have that entropy, the entropy of warming the solid, and then you would do the melting. You go up to the melting point, and now you know how to calculate that entropy. That is the entropy of fusion, and that's the reversible heat, and the temperature doesn't change for those processes. That's a beautiful example of a constant temperature process, only energy going into the system at a constant temperature. So we can calculate that entropy, constant temperature of melting, and then let the liquid warm up, use the heat capacity between the melting point and the boiling point to get that entropy, and then let it vaporize and add that entropy change, and then let the gas come up to a specific temperature. So if we had nitrogen gas at room temperature, that's how we would calculate the entropy, molar entropy of nitrogen gas at room temperature. We'd add up these various steps, and you know how to do every step in that calculation to get entropy changes for compounds. So the total entropy change is the standard molar entropy if you do this for a mole of a compound. And you can tabulate them, just like standard molar enthalpies of formation. You can do standard molar entropies. And we don't even put the delta in front of that because the zero state is 0. So this is an actual number you can arrive at, and everybody uses the same 0. So we call them molar entropies of formation. And of course, since it's a thermodynamic process, you can add up molar entropies of products minus the molar entropies of reactants, and then get a standard molar entropy change for a chemical process. That works for all our thermodynamic functions because they're state functions. State functions only depends on the initial and final state. Okay, I think that's all we have to do for this one. We'll do all the rest of this stuff in discussion. So let's go on to the next one, which is here. Give me a second here. Come on. Yep. Yep. Oops. Okay, we'll continue with our roadmap, still in the same place. We're talking about why reactions go. So the learning goals, as you know, you can go back and review those, make sure you know what's going on. Let's start out with a chem quiz at the triple point of water. Now, we've talked about the boiling points and melting points where the liquid and the gas or the liquid and the solid are in equilibrium. And those you intuitively know when you got here, so we've been brushing over it. We're going to talk about them in detail in a lecture or two. But there's also a point where the solid, liquid, and gas, all three of them are in equilibrium. What does equilibrium mean? Equilibrium means that the system can be in the liquid or gas state if it's boiling at the normal boiling point. And equilibrium means the universe is indifferent to which state you're in. You're going back and forth freely. So equilibrium is one of these rare cases where the entropy change of the universe is 0 between the gas phase and the liquid phase. The universe entropy is 0. So the universe does not care whether you're in the gas phase or the liquid phase at equilibrium. That's why we have equilibria. So you can be in equilibrium between all three of them. My question to you is, all three processes are happening at once. Solid going to liquid, liquid going to gas, gas going to solid. Which of those has the highest entropy change associated with it? Why don't you just vote on this one? I think this one, sometimes you think there's a trick and you got to overthink it. There never is. It's always straightforward, but it's new. This is not so new. Which of these is the greatest increase in entropy in the system? Going from the solid to the liquid to the gas, or the gas to a solid? Just go ahead and vote on that, and we won't even hide them. Just which one do you think is the highest entropy change? Okay, we have a lot of the middle one there. And the middle one is the liquid going to the gas. I agree with you, the liquid going to the gas. If you can do all these three things, solid going to the liquid going to the gas, liquid going to the gas, the most possible microstates are in the gas phase. So that's the greatest increase in entropy. The greatest decrease would be going from the gas to the solid. Okay, that's system entropy. Okay? So this brings up an interesting point. Why are these things in entropy? Why are these three states in equilibrium if the entropy change in the system is so dramatic? This has higher entropy than these two. Why doesn't the universe just favor the gas phase. And indeed, the universe favors particles spread out as far as they can be. That is the trend for the universe. But why in this particular case, equilibrium at triple point or equilibrium everywhere, is that the case? So the universe is indifferent. What do we mean by that? How can that possibly be that this case here, high entropy, this case here, low entropy and low energy, how can that be the case that all of these can somehow be at a level playing field in terms of the universe? And we know to get here, to go from the water to the liquid, we have to absorb energy. That's endothermic to do that. So this is the higher energy state. This one, when we form the solid, energy is released. That's the exothermic process. But we also know, well, that entropy change is very positive. That's the gas. And this entropy change should be negative. That's forming the ordered solid. So it doesn't look like those stack up. We wouldn't guess that somehow these can be on an equal playing field. And indeed that's the case, and we'll talk about this in a little more detail, but it would be nice if these two factors just cancel each other out. You know, this factor and this factor cancel each other out, and this factor and this factor cancel each other out, and then it would look like equal playing field. So if we could just take and say, well, let's just change the sign on that. Okay, multiply through by negative. So take the entropy change, multiply through by negative, and that starts to look like, so we take the opposite of the entropy change. Now it looks like those things will cancel out, and it looks like we'll be able to say energetically and entropically equal between all three states. And that is exactly what we do. We come up with a new state function that does that. But now if you say, oh, these are equal and opposite, these are equal and opposite, then you could say, energetically and entropically, these three changes, these two equilibria are equivalent energetically and entropically, and they could switch in between each other, interchange between each other at the triple point. So equilibria could occur if these two things balanced each other, the entropic and enthalpic effects. Let's look at that more carefully then. Here it is. Let's just look at one of the transitions, liquid going to the gas. So the liquid going to the gas, we're interested in the entropy of the universe. Why is it 0 at this boiling point? Why is the universe indifferent? Well, the entropy of the system plus the entropy of the surroundings is the entropy of the universe. For it to be spontaneous, it's always greater than or equal to 0 for that case. The entropy of the surroundings, easy to calculate because it is that enthalpy of vaporization. The system has, the surroundings has to give up this much enthalpy at the boiling point for the system to go. So there, the surroundings has a decrease in entropy. It's giving up its heat at constant temperature. The system is going from gas to liquid. The system increasing in entropy. And you could imagine those perfectly balancing. The surroundings entropy perfectly balancing with the system dramatically increasing in entropy, the surroundings decreasing in entropy because they're giving up that heat, and you can imagine those things coming into perfect balance and the entropy of the universe having this equal sign. The rare case it has that equal sign. And that rare case that has the equal sign is the equilibrium situation. The universe does not care. The entropy change of the universe is 0 for this transition. It doesn't seem like it because the system is going to higher entropy, but the surroundings is paying for it by giving it its energy. So these enthalpy of vaporization and the temperature, those are actually just system variables, though. The enthalpy of vaporization is a system variable. The entropy change in the system is a system variable. So I'm just going to multiply through by minus t here. So I'm going to have entropy of the system, or enthalpy of the system, minus t times the entropy of the surroundings, system, two system variables. And this is a fundamentally beautiful thing. I'm going to multiply through by that negative sign, so that changes this equality. Multiply through by negative, that goes from greater than to less than. And this is fabulous. This is the most beautiful result. We've been working towards this for 2 weeks now. This is why things happen. And these are both system variables. So we can tell what's happening in the universe by just looking at the system. That is fantastically powerful. We don't have to say, oh, this process is going on. I have to also measure the entropy change in the universe, the rest of the universe. That would be a pain, right? You don't want to have to track the entropy of the surroundings every time. These are two system variables that tell us about the entropy change in the universe. So they tell us, is the process favored by the universe? Incredibly powerful. It's the most beautiful thing, in my mind, in all of science and thermodynamics. So we should give this a name. Delta H, these are state functions, enthalpy, temperature, and entropy. So this combination is a state function. So why don't we give that state function a name and use that to determine the entropy change of the universe? Because that determines whether things happen or not. And we do. Two system variables track the universe entropy, and we do. We give that a symbol, a new thermodynamic state function, delta G, the free energy change of a process. It's called free energy because it is, just like our donuts today, not quite that kind of free energy, but it's the energy that can be used in a process. And you can kind of see that here. You do a process and some enthalpy change occurs. You burn fuel, you get all that energy out. You get that delta H out. But you cannot use all of it to do work. That's a fundamental property of the universe. That's why the universe is dying, in a sense. Every time you do a process, you lose this little bit to entropy, and that is lost into random motions, and you can never reclaim that and get that back and totally conserve entropy. So even if you go around in a circle, you can do enthalpy. You can say, I got to put all that enthalpy back in. Total enthalpy change 0. I went around in a circle. Total entropy change not 0 for the universe. I always lose a little bit to the universe, and that little bit of loss of entropy to the universe says I don't get to use all my energy efficiently. I always lose some of it. So the amount I can get out and do work with is fantastic, but a little of it always goes away. So that's why it's called the free energy. The energy I have, I can do useful work with part of the thermodynamic change. That's called the free energy. It's one of the most fundamental properties. And if the free energy change is less than 0, that means the entropy change of the universe is greater than 0. You notice we changed the sign here. So if entropy change of the universe is positive, the free energy change is negative. And that is convenient. So if I go down in free energy, I release free energy, that is not only a decrease in energy, which is good, but it is the natural direction of the universe. It encompasses both the entropic and enthalpic properties and tells us that's where the system ends up. The whole system is going to minimum free energy, not just minimum enthalpy. It's going to minimum free energy. So I like that so much. It's one of my favorite things. We were talking about sailing the other day. I named my boat Free Energy. In fact, I'll go over to camera 2. Can I go over to camera 2 and just talk directly to the audience? We'll do two things. If you're watching from home, can you get me on camera 2 over here? Give me a nice headshot. I'll talk directly to you in the live stream. Two bad things if you're watching live or remotely. One, you didn't get a donut. Oh, beautiful, beautiful free energy in donuts. Second thing is, can I have it up here? On my shirt, that's the logo for the boat. My boat's called Free Energy. And you can see in there, this squiggly thing, that's a lowercase delta. And a G next to it. So again, you're all welcome to come sailing. If you want to come sailing, if you're out there watching in TV land or here, you know Christina, she's one of our staff. Her email is on the website. Email Christina, say, I want to go sailing. And we'll just arrange some times. So she'll sort out the people that want to go, and we'll get some scheduled times where we can all go sailing. Christina and I and Charlotte were out last night on the boat. Beautiful sunset cruise. Actually, we can plug, why don't we just plug the program? I'll show you some. There's people on the boat. Here, these are, all those are teaching assistants from a couple years ago aboard the boat. Here are, these are all students from last summer on the boat. Here's the boat, and there's that logo, Free Energy, out in front of the house. That's just my puppy with the gal sweater on. That's just for fun. Here are 2 summers ago teaching assistants all lined up. We'll get all our teaching assistants, hopefully, out on the boat and get our group photo this year as well. So email, send your emails to Christina. She'll organize trips out. Okay, super important. The free energy change is the system enthalpy minus the temperature in Kelvin times the system entropy change. And if that is less than 0, that is negative, that is a spontaneous process. That's the favored direction of the universe. Okay, and also the name of a boat. So let's look at the various combinations of enthalpy and entropy and temperature. So since this thing determines whether things are spontaneous, whether they will go or not, whether it's the favored state of the universe, we should look at the various combinations, and Karen can do them. Karen, why don't you come out and we'll start doing some demos of these things actually happening. Endothermic processes, we just did one. We did one where it was very endothermic. We're going to do another one now. But you could do that with an increase in entropy of the universe, or, excuse me, of the system, or a decrease in the system entropy. You could go either direction. If you had this specific combination, though, it absorbs energy and the system entropy decreases, so it goes to lower entropy. Both of those things are what you would call bad for the universe. You don't want the system to have to go to higher energy. That's bad. It doesn't want to go to higher energy, but it also doesn't want to go to higher order, to lower entropy. So both these things work against you. And if both those things work against you, there's no temperature where you would find delta G is always positive for these. You can see it. If delta H is endothermic, what sign do we give endothermic processes? Delta H coming in, that's a positive energy change. Delta H is positive. Delta S, negative. You're decreasing the entropy. So a positive contribution to delta G, bad. You want delta G to be negative. A negative contribution here, but T is always positive. It's Kelvin. So that always turns that into a positive number 2. So those kind of processes never go for any temperature. And you can just look at the other combinations. Exothermic, negative, that's good. Less order, that's positive, so always negative. Good, good. So you have this good, good combination, and those are spontaneous. Delta G will be negative at all temperatures, no matter what the temperature is. And then there's the intermediate combinations. What if delta H is good, making this negative, but delta S is bad, making it positive? Well, then you have to go to a specific temperature to get delta G to be negative. So the temperature matters. You have to make the entropic part big in order to get delta. If delta S is big and positive, then delta G will be negative. If this is already positive, then you have to go to small temperatures to make sure this part is smaller for an exothermic reaction than the entropy. And there it is. You're looking at entropic and enthalpic combinations, and you're separating the two parts to see if the universe is favored. And of course, the other combination will happen at high temperature. If it's endothermic, that's bad, but endothermic, that's a positive contribution. Delta S greater than 0, that's a good combination because it has that minus T there. If you go to a high T, the entropic contribution wins. And this whole minus T delta S becomes bigger than this plus delta H. And overall delta G will be negative and those processes will go. So Karen can show us some of them. The first one looks like, potassium and water. Karen, can we do that first? So here, let's just look qualitatively. So I'm going to take solid potassium and liquid water. I'm going to make potassium ions, hydroxide ions, and hydrogen gas. If I do that, I can kind of predict the entropy change for that because I'm producing gas from the solid and liquid. So you can probably predict delta S for the system very positive. And Karen can do it, and the fact that Karen has put up shields indicates that delta H is probably negative. It's going to release energy. So delta H is negative, delta S is positive. That means that's good for the universe. That's good for the universe. That tends to make delta G negative. Minus T times that tends to make delta G negative. This delta G will always be negative, spontaneous at all temperatures. So Karen, let's look at that one. So she's going to take metal potassium, a solid piece of metal, drop it in water, and look at that. It immediately reacts. Why did it explode? That was a beautiful one, Karen. You should get that one every time. Why did it explode? Because it was producing hydrogen gas, and you know hydrogen gas will explode in the presence of oxygen. The heat released, the enthalpy of the reaction ignited the hydrogen, and Karen will rinse the extra potassium. That's cool. You rinse the potassium off and just have it just react on the glass too, or on the shield as well. So let's look at another one. Here is water, liquid water and oxygen gas forming hydrogen peroxide. Okay, we can't do that one directly, but let's analyze it. If you go liquid water and oxygen gas and form a liquid, if you looked at delta S for that, you would say, well, that's a reduction in entropy. I take a gas, I make a liquid. If I look at the enthalpy change, that is going endothermic. So you would say delta G would be positive for all temperatures, because that always helps you, and or that always hurts you. And if you take minus T and multiply it by that, that always hurts you and makes delta G positive. So this is not spontaneous for any temperature, but we can do it in the other way. Going this way, that means it would be spontaneous at all temperatures. Go in that direction. So let's just do it in reverse, the fun way. And Karen can do that by adding, here is the peroxide liquid. She can add a catalyst, so the reaction goes rapidly. Doesn't change the energetics, we'll learn that. Doesn't change the enthalpy, just changes the speed of the reaction. So go ahead and add that manganese, I think, oxide catalyst to peroxide. We'll get a picture. We got a picture for you, Karen. And yes, spontaneous in this direction. And that's producing, as we can verify, yes, oxygen gas. I have very sensitive nose, after many years of detection. All right, let's look at another combination. We'll take aluminum bromide, decomposing into aluminum solid and bromine. We'll do that one in reverse. Can we do that one in reverse, Karen? So she's going to do it in reverse, this direction, by taking some metal. Get that on the camera while she's setting that up. She's going to take some metal, and that will represent, that foil will represent the aluminum solid metal. The bromine liquid, she will pour into that giant beaker as soon as we get some light on that. Can we get some light? There we go, lovely. So this is bromine, liquid bromine poured on top of there. It's starting to evaporate, the bromine liquid, but she will mix those together, the metal and the liquid, and look at that. The metal and the liquid start to react exothermically. And your form, ooh, that is really cool. Oh, look at that, and then she's pouring the gas. Karen, tilt that and pour the gas down the hood again. That was really cool. Excellent. So you're forming in there aluminum bromide, the solid. And if you looked at those, you might say, well, you've got liquids forming solids. So going in that direction, you would expect the entropy change to be positive. You'd expect, we already saw it, that the reaction going in this direction is exothermic. So that direction is endothermic. So that's one of these where endothermic, that kind of hurts you. That tends to make the delta H positive, or makes delta G positive. Minus delta S, you can make this one negative. You can make it more negative at higher temperature. T delta S can be negative at higher temperature. So at high temperature, you could get delta G to be less than 0 and be spontaneous in that way. We'll do one more. We're going to take magnesium solid, carbon dioxide solid, and make magnesium oxide and carbon solid. And in this case, it's not really even clear. It's hard to tell just by looking at it what the entropy change is. You just got a bunch of solids changing places there. And you could get out your tables of standard enthalpies of formation, and you could calculate the enthalpy change for this. But I'll tell you, we're going to do it in this direction. So I'll tell you, it's exothermic in that direction. And what Karen has here, we can get that up on the screen. There's your solid carbon dioxide. And that's dry ice. And after Karen gets this going, if we could bring the lights down so we can see the reaction going. Is that magnesium powder?
Powder dry ice.
Oh, powder dry ice. She's getting a little dry ice, crushed dry ice to get a better contact between the magnesium and the carbon dioxide. And then she's going to take some magnesium metal in that beaker there. That's magnesium metal. Pour that in there. That's just solid magnesium. We've seen that burn already. Now, what she's going to do is she's going to do kind of a fire extinguisher thing, right? Because basically you're going to make carbon dioxide gas there, and that should put out any fires, right? So you would think that she should be able to stop the reaction by putting in lots of carbon dioxide. But let's see what the universe has to say about that. First, she'll start the magnesium glowing, and then can she put it out? Can she stop the reaction by covering it with carbon dioxide? And look at that. Can I bring the lights down in the auditorium a little bit? Look at this. That reaction continues to glow and heat and just emit energy as heat. That magnesium continues to burn enveloped in carbon dioxide. So what you have here is, can you bring the lights in the auditorium down, especially this one here in the front, see if we can get some of that glow? You can see that glowing in there. Is it possible just to tilt that a little bit, Karen? So they can see the glow, just tilt the whole thing towards the camera just a bit. It's starting to, the reaction's starting to stop already. What you see there, though, is burning magnesium in solid carbon dioxide. It's fire, it's literally fire and ice. It's yin and yang of chemistry coming together. The universe says that this is downhill in free energy at low temperature. So that reaction is spontaneous at low temperature, and you cannot prevent that reaction from happening at low temperature. Carbon dioxide doesn't extinguish that flame. It allows that flame to go. Low temperature, the reaction is negative delta G. High temperature would be positive delta G. So you go to low temperature on carbon dioxide and it burns more. That is an interesting oxidation reaction, to be sure. Pretty much one of my favorite reactions. So let's see if you're following along. I have in here, and I'll just stand. Do I have my confidence camera on here? I can't see myself. Down here, I don't know what the camera shot is. Camera shot here of me. I have in this flask NO2 gas in equilibrium with N2O4. The NO2 is brown, so you can see it in there. But it's this dimerization is at equilibrium in this flask. And I want to tell you, if I write it like this, what is delta H for this reaction as shown? This reaction as shown, going from the monomer to the dimer, that is spontaneous, I'm telling you, at 25 degrees C. If that's spontaneous at 25 degrees C, what can you tell me about the enthalpy change? Standard state enthalpy change. Talk about that among yourselves. TAs, GSIs, get up and let's talk about that one. among everyone in the room. Okay, I'll turn on the machine. You can vote on this, see what you're thinking. There are some things to think about if you haven't thought about them already. Go ahead and register your thoughts as you're thinking. If you need a few more hints. So while you're voting, let's talk about these three possibilities. Delta S is less than 0 since the number of particles decreases. So it must be exothermic to be spontaneous. Interesting argument. Let's look at, I like that argument. Spontaneous reactions do not release or absorb energy, so delta H is 0. That's just garbage, right? I think everybody would have thrown that answer out. If your neighbor said that, you would have said, no, spontaneous reactions, they can absorb or release heat. That's fine. All that matters is delta G has to be negative, then for the universe has to increase. Bonds are formed, so it must absorb energy. Is that true? Bonds formed absorb energy. Do those two things go together? No, they always go the opposite way. If you take nothing else home from Chem 1, take home the fact that it requires energy to break bonds. So if you form them, what happens? Energy is released. It's always exothermic to form bonds. Take that one to the bank. Those two aren't true, so this top one must be true. And you could have seen it here. So we'll look at how you guys voted. Well, now you know the answer, so you could change your answer. But you guys are thinking the first one here. And the first one was that it is delta H Less than 0, it's exothermic, so that's correct. Why is that? Lots of ways to think about it. I told you it was spontaneous. So what is the sign of delta G? Negative. You can infer delta S. Why can you infer delta S? Don't go to bonds. If you're going to go delta S, don't go to bonds. What? Less what? Lower microstates, why? What? Fewer particles, yes. Fewer particles is always fewer microstates. You go from 2 particles, half the number of particles. Half the number of particles, lower entropy. So that is a more ordered system. So delta S, entropy decreases. So the sign of delta S, negative. But if you're talking about delta G, it's minus T times that. So going to more order is bad. And you know that. Yes, going to more order, even in the system, is bad. That hurts your chance of being spontaneous. So that's a positive contribution to delta G. You need a negative contribution to delta G. You've got to get one. If I told you it's spontaneous, and I did. So the free energy is delta H minus T delta S. Delta S less than 0. That means minus T delta S is positive. That hurts your chances. This must be negative. The enthalpy has to save you to make it spontaneous. Okay? So this is enthalpically driven. If you looked at this and said, does entropy help this go? No. Because entropy is being reduced. Does enthalpy help you go? Well, you don't know unless I told you about delta G, or is that true? What is happening here? Do you think there are more bonds over here than over here? What it looks like is, dink, dink. What it looks like is the formation of a bond, doesn't it? And it is. A bond is formed there. And if a bond is formed, what happens? Energy is released. And that's tough. I know it's hard to get through the head, so just always think about it in the opposite direction. To break it, I have to put energy in. So if it's formed, energy must come out. That one you can take to the bank. Good job. So the Gibbs free energy tells me whether a reaction is spontaneous or not. And we just looked at the spontaneous process free energy less than 0, but it has 2 contributions, enthalpy and entropy. Going down in enthalpy is good. Going up in enthalpy is bad. We know that. And that positive, endothermic, tends to make that positive. So if you're going up this hill, you better be going up this hill too. You better be going to more entropy, because that minus T delta S, this contribution has to outweigh that contribution and make delta G overall go downhill. So delta G is our low energy state. That's how things are determined to be stable. Going anywhere else, you have to increase free energy to leave that state. Everything ties together beautifully. You could put everything in the standard state. And if you're thinking about the exam, 2 gases in here. If it were in the standard state, what would be true in this flask? Think about that. It's a question on the exam. Delta G is a state function, so I can do this. I can tabulate free energies of formation of products and reactants. And because it's a state function, I can get arbitrary. I can get free energies of formation from tables. I'll just talk you through this one and we'll end on this. Boiling water. What's the correct plot of delta G versus T? And you know this is how I'm going to ask you on the exam. Why is that? Because it's hard to Google a line. It's a figure and you have to draw it. In fact, on the exam, not this one because we haven't got to this yet, but on the exam, I will give you 4 points, A, B, C, D, and I'll ask you through which 2 points does the line go? And you'll notice if I give you these 4 points, you can draw every combination of positive or negative slope or positive or negative intercept. All 4 combinations, all 4 kinds of lines, just schematic lines. Positive slope, positive intercept, negative slope, negative intercept. You can draw all 4. And that's what you see, that's what you're looking for. Here, negative slope, negative intercept. Positive slope, negative intercept, not y-intercept. Positive intercept, negative slope. And delta G is linear function of temperature, right? Delta G is a linear function of temperature. Delta H and delta S are constants with temperature. They don't change. So these 2 things are constant. So it's y equals mx plus b. It's the equation of a straight line. The slope of the line is the entropy. The intercept is the enthalpy. So if it's exothermic, that's delta H negative, you would have a negative y-intercept. If delta S is positive, the overall slope is negative because of the negative T, so you'd have a negative slope. Okay, so you can say this reaction in this direction, liquid going to gas, is that endothermic or exothermic? That you have to know, and you know that just intuitively. The gas is higher energy, than higher kinetic energy than the liquid. You put in that energy, that's endothermic. Boiling is absorbing energy. Boiling is endothermic. So the sign for endothermic reactions, delta H positive. A gas is produced, so you can look at that one and you can intuitively say the sign of the entropy. That's entropy increasing, delta S positive. So if delta S is positive and delta H is positive because it's endothermic, positive intercept, negative slope because of that negative sign, positive delta S, negative slope, and that one looks like, here we have a negative slope and a positive intercept. Here we have a negative slope but a negative intercept. So this is delta G as a function of temperature for that system. So it's one of those cases where, is this spontaneous at high temperature or low temperature? High. Why? Delta G goes negative the higher you go in temperature. There it is, plotted out. What do you think that point is? That's where delta G is 0, so the universe is indifferent to whether it's the liquid or the gas. So what temperature do you suppose that is? Any guesses? The natural boiling point. Yeah, where it would be equilibrium between the liquid and the gas. All right, we'll see you guys tomorrow. You have an exam tonight. Good luck. I'll have a discussion at 11 in this room.